¿qué les puedo decir? Navegando por todo el globo terráqueo, acabo de cumplir 43 años de servicio en la Marina, de lo cual me siento muy orgulloso. Y pues he navegado en el 90, le dimos la vuelta al mundo y siempre he visto el agua como un recurso de comunicación, como un medio de comunicación y un recurso vital pues para los marinos. Y ustedes pues saben mejor que yo eso, el cuidado del agua. No les robo mucho su tiempo, simplemente quería saludarles, felicitarlos y honrar este momento tan valioso que este plantel con el director les facilita este foro para que ustedes desempeñen aquí en beneficio de nuestros países, porque es un alcance internacional. Quedo a sus órdenes en Ensenada. Quiero decirles que la Secretaría de Marina trabaja las 24 horas con los 3 niveles de gobierno. Aquí en el estado venimos ahorita de una ceremonia muy bonita que presidió la diputada federal Nadia Sepúlveda García, y fue el inicio de una jornada de paz donde se simbolizan unas esculturas emblemáticas construidas de armas que son decomisadas y destruidas. Entonces hay un autor, un artista que materializa esos instrumentos que anteriormente eran violentos y que hacen una transformación, un reencuentro con la naturaleza, y convierten ese hierro en un símbolo de arte para reflexionar. Pero bueno, no me alejo del tema. Les agradezco este momento, señor director, a usted y a todo este personal, y siéntanse muy felices de estar aquí, muy honrados, y estoy a sus órdenes en Ensenada. Muchas gracias.
Muchas gracias. Pues esta es una de las nuevas formas que tenemos en este país y que representa una gran transformación, ¿no? Entonces, gracias por esta intervención, y pues ahora vamos a dar paso a la parte académica. Le voy a pedir a mi compañera y amiga, la doctora Virginia Hernández, que nos presente a la primera conferencia plenaria. Gracias.
Muchísimas gracias, doctora Teresita. Buenos días a todas y a todos. Bienvenidos al primer Congreso Internacional en Agua Limpia y Saneamiento del Tecnológico Nacional de México. Good morning. Welcome to the first International Congress on Clean Water and Sanitation. The first plenary speaker is the PhD, Satinder Kaur. She is an important research in the world. In some aspects of their work are summarized in Spanish for easy comprehension. La doctora Brar es una investigadora reconocida a nivel nacional e internacional con una experiencia excepcional en 2 campos de la investigación. Número 1, la valorización de residuos y la eliminación de contaminantes emergentes. Sus investigaciones han trascendido fronteras y ahora se adaptan a nivel mundial. Por ejemplo, su investigación sobre biopesticidas y biofertilizantes que utilizan aguas residuales se aplican ahora en Vietnam, en Marruecos, en Costa de Marfil, en Tailandia, en México y en India. Se le han otorgado numerosos premios y distinciones nacionales e internacionales por el impacto de su investigación en términos de tratamiento de agua y calidad. Recibió el International Women Research Award en 2019 y la medalla Process Wastewater, honrada por the Water Environmental Federation. En 2017 recibió el Gran Premio a la Investigación Universitaria a la Excelencia en Ingeniería y Ciencia Ambiental de la Academia Estadounidense de Ingenieros y Científicos Ambientales. Actualmente la doctora Brar es profesora investigadora de la Universidad de York en Canadá. Tiene 534 publicaciones y más de 20,000 citas. Satinder, it's an honor that you here. Thank you very much. Please continue with the presentation.
Thank you. Thank you so much. Okay. Yes. I'm ready? So, a very good morning to all of you. Buenos dias. First of all, I would like to, sorry. First, I would like to thank Professor Hernandez, for inviting me to this conference. And Risita, Professor Sarmiento, who have been so warm in their hospitality to get me to this place. And by the way, this is my 4th visit to Mexico. I really love Mexico for their warm hospitality. It's a great country. Okay, so let's begin. I'm going to talk about microplastics, as you see here, in sewage sludge exploration and detection. So, we put these plastics down the drain and they're out of sight and we forget them. But that's not how the story should end. Okay? So before I begin my talk, I would like to give you a brief introduction about my university. I come from York University that has almost more than 10,000 students from 172 countries, and Toronto is the most multicultural city in the world, okay? And we have almost more than 54,000 students studying different disciplines. And then, of course, we have 3 different campuses within Canada in Ontario, and we have 2 international campuses, one in Costa Rica, that is called the Living Lab campus, and the other one is School of Business in Hyderabad, India. And I come from specifically Lassonde School of Engineering. My home department is civil engineering because I'm an environmental engineer. A bit about myself. I was born in Bangalore, so my origin is Indian, South India. And because my father was in the Air Force, so I had the pleasure to travel the country and studied in many places in India. And I did my bachelor's in chemistry honors, then I moved on to master's in organic chemistry, and that's where my interest in environmental engineering started. And finally, I did my master's in environmental engineering from Indian Institute of Technology in Bombay, and then I worked for 2 years as a defense scientist in the defense organization in India. Then I did my PhD in biochemical engineering in Quebec in Institut National de la Recherche Scientifique. And of course, then I started my faculty position at INRS for short from 2007 to 2018. And then 2019 onwards, I've been at York University in Toronto. Okay, now let's jump to my research philosophy. What do I do? So this is what I do. I work on water resource recovery, recovering whatever possible resources we have in water. I work on holistic treatment. Holistic treatment means, you design treatment technologies only with the objective of having higher efficiency. But getting higher efficiency is not our objective. Our objective is to get to something which would be potentially less toxic. Okay. Then I work on contaminants, all sort of contaminants from, conventional pesticides to the microplastics, which I'm going to talk about today. And then I have another field that is called the bioproducts field, where what we do is we bring different kind of residues and we transform them through fermentation to different bioproducts, enzymes, biopesticides, biocontrol agents, etc. And this is the team that has been working, because this is a big project that I'm leading on microplastics. We have Dr. Rama Pulicharla and Dr. Das. Both of them are postdoctoral fellows. And then we have graduate students, Juvia, who is working on the detection of microplastics, Gaurav and Mariam, who are working on the secondary treatment in the wastewater treatment plant. Anastasia is working on anaerobic digestion, and Benam is at the end of the pipe treatment, that is, he's working more on the river water. So let's dive into the topic now. To begin with, the plastic world, everybody knows plastics, right? It's not something new now. And worldwide, almost 90% of the plastics, that are released, they are not recycled. I don't know what is the recycling scenario here in Mexico, but even in Canada, we are not able to achieve 10% recycling. The scenario is so bad. And let's talk about the release of microplastic, use of plastics. So in Mexico, it's 66 kgs per person per year. And the picture is really bad in Canada and US. We are almost double of you, almost 130 to 150 kilograms per person. So that's not a good scenario at all. And if we talk about plastics, it's the microplastics which become a bigger problem. How? Because the size matters. You start from macroplastics where the size is more than 25 millimeters. You're going down to microplastics where it goes down to 5 mm. And then nanoplastics is something which we cannot even see. And that is something we cannot even imagine what could be the impact of it. And of course, when we talk about the origin of microplastics, they can be primary as well as secondary. If we talk about primary microplastics, they could be the microbeads. We use a lot of microbeads in personal care products. Your exfoliants, they all contain microplastics. Okay, then it can be plastic pellets from industries. Then we have secondary microplastics because you would have heard about a lot of plastics getting washed on the marina. So that all is also undergoing weathering or fragmentation and getting transformed into microplastics. Then we have microfibers. When you wash clothes in the washing machine and you dry them, a lot of fibers are generated. They are all microfibers which contribute to the microplastics. Then we have films, okay? And of course, we cannot ignore the tire wear particles. The tires are made up of synthetic rubber, and synthetic rubber has a lot of plastic in it. So when continuous weathering is happening, and like in a country like Canada, where our public transport is dismal, we use highways a lot. So we use a lot of cars are going on the highways, and a lot of these tire wear particles are being generated all around the year. Now what happens when we talk about the microplastics generation and how are they actually getting into our bodies? So let's first talk about persistence. So all of you know microplastics or even plastic bottle as such sitting around in the ground, it will take more than 100 or even 300 years before it can really biodegrade or degrade, okay? And of course, I'm sure you guys consume fish, so enhanced consumption of this marine food is another source of microplastics getting into our bodies. And of course, if some of you are biologists, you would understand it gets bioaccumulated, and eventually the concentration goes on increasing across the food chain, and then it gets biomagnified. So we have human health risks. There are a lot of studies published around this field. I'm not getting into that, but that's why it becomes important to study the microplastics. Now here in Mexico, I dug some data. Apparently in Mexico, individuals ingest 71 milligrams microplastics per day, which is like 15,000 microplastics per day. And especially if you eat a lot of junk food and those fast food centers or restaurants, they give you those plastic containers, polyurethane containers. So the microplastics are leaching out into your food through that as well. So in other words, microplastics are omnipresent. They are present in the air, water, and food we eat. That's why it becomes important for us to study and understand how they manifest. Now let's get from the general scenario of plastics to the wastewater treatment plants. Why am I trying to study wastewater treatment plants? What is the connection with food? What is the connection with water there? So first of all, let me present to you an earlier view of the sanitation infrastructure. Technically, before the 1900s, or even in the early 1900s, it was thought to be an end-of-pipe waste removal. You flush out toilet, it goes to the wastewater treatment plant, and the wastewater treatment plant must take care of it. I don't care. It's out of my sight. There was limited pollution control, so the discharge limits were also not controlled, and the water after treatment was being discharged everywhere. But now, since the 1990s, the scenario has changed. We call them urban resource hub. because we want to protect our water resources. In fact, in many countries, not yet in Canada, but at least in US, for example, in Arizona, they treat the wastewater and they re-inject the effluent into the ground and then use it as a new water, for drinking. So it's naturally a resource. And of course, we lose a lot of nutrients in the wastewaters, which we want to recover. You have heard about, recovery of struvite, nitrogen, phosphorus. So all this is happening through the wastewater treatment plants. And of course, the most important is we want the wastewater treatment plants to be resilient so they can, resist any changes that are happening in our wastewaters. Because you would have seen that the plastics scenario has really exponentially increased ever since, I think, the 1980s, though it was after the Second World War that the plastic usage really increased, but it has really reached alarming levels, I would say, at this point. So normally, why do we want to study wastewater treatment plants is because wastewater treatment plants, they constitute a defense, if you want to call them, frontline defense against water scarcity. I talked to you about the reuse of treated water, any climate pressure, and emerging contaminants such as microplastics. So henceforth, if you find MP means microplastics. And a single wastewater treatment plant here in Mexico, according to one of the studies that I found, they released 101 to 172 billion microplastics annually in Mexico. So you can say a fairly large load of microplastics, they get into the wastewater treatment plants, and eventually they are released through the treated effluent back into the waters. So how does the journey for the microplastic begin in a wastewater treatment plant? First, we start with the raw wastewater. So imagine you have 100% microplastics or nanoplastics. Then you have the primary treatment, where you have the screening step and the sedimentation tank. So almost 70 to 80% of microplastics are removed here. WP refers to weathered products, that is the weathering of microplastics into fragments. And then 20 to 30% they move into the secondary treatment, where you have aeration tank and sedimentation tank. And then 10 to 15% they get into the tertiary treatment, where you have filtration and disinfection. And less than 10% are actually released through the effluent and reach the river. However, 50 to 60% of the microplastics, they end up in sludge. So anaerobic digestion and dewatering. And more than 90% of the microplastics of the entire wastewater treatment plant actually are present in the sludge. So I don't know what is the scenario. I think in Mexico I found some papers where you still apply biosolids as fertilizer in agriculture. So in other words, we are bringing it back to our cycle, okay? So the microplastics that are present in the sludge, they would eventually end up again in the agricultural soils. So you could say this 90% that we missed, actually we did not miss them. It's just that they moved from one compartment to another. Okay, so let's talk about the missed project. That's what we call as the components. So we have the influent first. Then we try to develop a detection and characterization method, because without detection method, you cannot analyze the microplastics. Then we go to the secondary treatment. And if you are aware of wastewater treatment plants, we have biofilm formation in wastewater treatment plants, and it becomes very important to understand their transport, fate, and impacts there. Then we get to the contribution of biofilm as a source to spread antibiotics. You know, antibiotic resistance is a big problem, and microplastics in some way, they are one of the contributing factors to the antibiotic resistance. I'll let you know as we move further into my presentation. And of course, then we get to the sludge treatment, where the weathering of microplastics happens in mesophilic temperatures, because we are talking about temperatures of 40 degrees Celsius, 40 to 60 in anaerobic digestion. And then, of course, the effluent, it goes to the fresh water. So we need to understand what happens once the effluent is released into the fresh water. In this study, we studied the Lake Ontario, which is one of the big 5 Great Lakes, we have in Canada. And we studied also harbor because we have a lot of industries localized around this Hamilton Harbor in Ontario. And I'll show you the outcome of those project components. So let's begin with detection. Detection is a very critical part of any kind of contaminant analysis, okay? And this is not easy to do, as I was discussing with one of my colleagues here. So why do you think detection is important? Because, you know, we need to explore and understand how these microplastics, they manifest in the different wastewater treatment plant unit operations. It starts with sample collection. Now you cannot collect your samples in plastic containers, so you need to have steel containers, and they are heavy, but we had to use them. And then you bring the sample to the lab, you do digestion, we have density separation, filtration, and finally we try to do qualitative and quantitative analysis for microplastics. So the research questions that arise and which are very important is there is no standard protocol for microplastic analysis, okay? So you have to first understand that when you transport the samples, they need to come in this is a milk canister, by the way, stainless steel. We have to bring samples in this, and they are heavy, these canisters, okay? But we have no choice because we don't want to have biased results, okay? And then storage also becomes important. How long are you going to store these samples? Are you going to freeze them? Are you going to just leave them at room temperature? Are you going to put them at 4 degrees Celsius? All that matters. And then when you get to the wastewater treatment plant, where should you sample? Should you take a grab sample? Should you take the samples all through the year? Should you be taking sample every day, every week? All this is part of the logistics, okay, when we do the analysis. And of course, what are the steps? So this is what we do in our lab. We bring the wastewater or wastewater sludge, and we have developed ultrasonication method using penton oxidation. After digestion, because we do not want any organic matter, there's a lot of organic matter in wastewaters and wastewater sludges. Then we vacuum filter these samples, and we optimize the parameters by suspended solids response. Once we have optimized the parameters, then we vacuum filter, we wash the residue many times using milky water, we do density separation, and then we have done the quantitative analysis using LDIR. Okay, so LDIR is a laser infrared imaging technique. This is the closest we could get to the quantitative estimation. Now what happens is when we are optimizing, it is very important we have to optimize the peroxide concentration, the amplitude, and the time. So you can see the experimental value was almost matching the predicted for the suspended solids, which is interesting, and these were our optimal parameters. Moving further, when we did the LDIR analysis, this is how the LDIR analysis looks like. So you have number of microplastics on the y-axis, you have the size distribution in micrometers here, and these are the different legends for different kind of microplastics. So you can see we have, humongous quantity and number of microplastics, because we are talking about wastewater treatment plants. Whatever we use at our home finally gets to the wastewater treatment plant or landfill, okay? So whatever you throw in the bin gets to the landfill, whatever you throw in the drain goes to the wastewater treatment plant. So here we had surprising results, because if you will look at the data of plastics that are produced across the world, polyethylene is the most manufactured plastic across the world. But what did we get? We got polycarbonate, which was present in higher numbers all across the different sizes. Likewise, polyurethane was another component which was highly present. Now, I cannot say this about Mexico, but in Canada, apparently, polycarbonate is something which seems to be used in higher quantities. That's why we see more release of polycarbonate in the wastewater treatment plants. And here, most important thing I have to tell you, this is very fancy figured, easy to see for you, but this is almost 3 years work for the student, because she had to repeat many times. You can have a lot of variability in wastewater treatment plants. You know, it's not just one run and you get the results. So we had to compromise, I should say, with, you can see the confidence level was just 70%. Okay, more than 70% was good to go for us. And further on from here, where are we moving? Now our objective is we are trying to reduce the sample preparation time, because normally at present we take almost 16 hours, the entire sample preparation. We are trying to reduce the quantity of chemical reagents because we don't want to use any harsh reagents. We are also developing some natural dyes, you know, which can help us dye these microplastics and detect them properly. Likewise, I have colleagues in mechanical engineering who are developing sensors, and I work very closely with them if we can develop sensors. Of course, sensors could be, you know, the ultimate thing if it could be done. And we are trying to develop an eco-friendly pretreatment approach where we do not want to have any secondary contamination. Remember, I told you one of my research components of philosophy is holistic treatment. So holistic treatment doesn't mean that you just do the treatment and be happy that I got 80% efficiency or 90%. You have to see what did you get, because these are organic compounds. They don't disappear in the air. You know, they get transformed into something, and that transformation is important to note whether it is toxic or not. And then of course, last but not the least, we want to have 100% recovery efficiency, because at present we are, I think, only reaching 80 in terms of recovery, okay? And especially our target is to achieve 100 micron microplastics. And moving further, so optimizing the pre-treatment protocol is on our books, and also trying to sample the treatment stages during the different seasons. Because in Canada we have these, we have the winter, fall, spring, summer. So the load of microplastics that is going into the wastewater treatment plant, it changes. So currently my student is trying to get a sample every week from the wastewater treatment plant and trying to see how the microplastics manifest in the different unit operations. So the final objective is to develop a sample preparation protocol which will help us monitor the microplastics in wastewater treatment plants in the wastewater and sludge. Next, we have to understand, does the biofilm formation in wastewater treatment plants affect their fate and transport? This is very important because biofilm systems, all of us, you have heard of, you know, membrane bioreactors, moving bed biofilm reactors. They are interesting configurations if we talk in terms of removal of COD, BOD, etc. But do they help in microplastics as well? That's what we wanted to understand. So Gaurav took this journey, and we have some, you know, physical-chemical aspects of microplastics which are important to understand, because these properties can change when you have a microplastic and there is a biofilm formation on the microplastic. Sometimes it can increase the roughness of the microplastic. So, and the hydrophobicity can also decrease because the biofilm is now sticking on the microplastic, okay? So we found so far from results that the biofilm is beneficial because it increases the microplastic removal, because now the microplastic can sediment in the sedimentation tank, and there is enhanced organic matter and pollutant degradation. But at the same time, it is detrimental because it starts to biofoul the membranes. So now you have microplastics as local nuclei, you know, floating around in the system, and they contribute to the biofouling of the membranes. And we have also seen it leads to reduced disinfection in the tertiary treatment. So that means you need more disinfection there. Likewise, we have the ecotoxicological and human health impacts. So the biofilm now is acting as a carrier for microorganisms. And some of these microorganisms, they can be pathogens, you know, disease causing. Likewise, you can have antibiotic resistance bacteria or genes that are getting transferred. So long story short, there could be this trophic transfer happening, and biofilm could be a big contributing factor to the trophic transfer. That's what we want to understand here. So what did we do is we because, you know, in wastewater treatment plants, every treatment plant is different. In Canada, we have these two important configurations, sequencing batch reactors, okay, in some systems. Then we have trickling filters, we have batch systems, we have attached film systems, we have the activated sludge, suspended growth systems. So it was important for us to compare, intercompare, and understand how the microplastics manifest in these different configurations. What do? We try to, you know, first work at a small scale. We have these flasks where you can see polyethylene, polypropylene, polystyrene, terephthalate, polylactic acid. This is supposed to be a biodegradable plastic. We enrich them every day, we incubate them, and then the biofilm is formed on the microplastics, where we determine the biofilm biomass assay, the colony forming units. We do the microscopic analysis. We also analyze the microbial community, and in the sludge, we determine the COD and nitrogen removal, the polysaccharide, because EPS is very important in biofilms, and do the microbial community analysis. So what did we observe when we, you know, had these different microplastics? You can see here, we did this study for a month because the biofilm formation takes time. And here is the optical density at 595 nanometers. This is an indirect parameter which explains the biomass formation. So you can see, as we move from polyethylene to polylactic acid, the change in the microplastic over 30 days affects the biofilm formation. So you can say polylactic acid is favoring the biofilm formation, okay? Now polylactic acid is assumed to be biodegradable, but it is not, okay? You can try an experiment yourself in the lab. You can keep the flask even for a year, nothing will happen, okay? This is what we saw. So in other words, polylactic acid is actually favoring the biofilm formation because of the fact that it has, you know, carboxylic acid groups, and that helps in the adherence of the biofilm. Moving on, then another parameter which is very important for us is the COD. So we wanted to see if the soluble COD gets affected. We have the removal of the COD on the y-axis, again the microplastics on the x-axis. So you can see as we move from the control, again polylactic acid affected the COD removal. So polylactic acid actually, you know, being less biodegradable, what happens is there are some inhibitors within the polylactic acid composition which start to affect the SCOD removal. So there is a lot of bias in those results, if you see. So that's why we saw continuously that the SCOD was getting affected due to the presence of polylactic acid. And then, of course, how do we do this? We have been, this is how the system is set up. You have a clarifier, you have return activated sludge, ASP, then the moving bed bioreactor, and then the feed. So we are working with real wastewater system, okay, and getting the sample almost, enriching it every week. And now a long-term impact that we want to study is the biofouled microplastics in the activated sludge process and the moving bed bioreactor. Next, moving on from biofilm, we want to know if biofilms are actually acting as vectors to spread the antibiotic resistance. So Mariam, what she does is she first tries to understand whether microplastics can actually act as carriers for different microorganisms. So it again starts with the properties, the physicochemical properties of the microplastics. You know, they provide a very good surface for the biofilm to form, and now they carry the antibiotic resistance bacteria and antibiotic resistance genes, and they are propagated through horizontal gene transfer. And then of course, this ARG is also transferred trophically to other organisms like fish, and we feed on them. So the ARGs is going through a cycle, you know, from the ecosystem to the fish to the humans. And what is the complex interplay which is important between the biofilm, microplastics, and antibiotics, I would say is they act as vectors. You know, they are the surface On microplastic, anything can adhere. You can have antibiotics, you can have pathogens, you can have ARBs, phytoplanktons, and then, of course, they are acting as persistent pollutants, whereby they carry these, pathogens from one part of the water body to another. Now, what do we do in the lab or even in the field is, this is Mariam, she gets to the wastewater treatment plant, and you cannot see here, but they are those tea, the tea filters they use, stainless steel. So we put the microplastics in them with a sieve and we suspend them in the wastewater drain. You can see here, this is the one that is used for teas, and then she leaves it for almost 3 months there, okay? She studies all across the chain, from the influent to the final effluent, what is happening to the microplastic and the antibiotics. So these are the parameters she measures, okay? So, yes, she has the microplastic particles. Sorry, I'm so sorry. She's trying to adjust something. It's okay. I can start? Okay, sorry for the brief interruption there. So getting back to this, what are the parameters we measure? We start with, like I told you, sit for 2 months to almost 3 months, then brings the samples back. She studies the physicochemical parameters and the ARGs, or the antibiotic resistance genes, and she also does Illumina sequencing and antibiotic quantification during LCMS. And this is also done on a seasonal basis. So this is an annual study. We start from winter, we go up to fall. And the samples are collected every week. And this is what she saw in terms of biofilms. So you can see these are the virgin microplastics, and this is the secondary effluent and the final effluent. So in the secondary effluent, there was a dense, complex biofilm formation. But in the final effluent, there was a moderate biofilm growth, which is normal because you're moving from more microorganisms to less microorganisms as you move from secondary effluent to the final effluent. And then, how does she analyze the antibiotics? So she goes through the solid phase extraction steps and then gets it analyzed on LCMS. And this recovery is, we are getting a very good recovery, you can say there. And the microplastic biofilm final optimization in process. Because biofilms are very difficult to extract in terms of antibiotics and microplastics. What is next? Well, we are here. So she is in the data analysis and advanced molecular techniques. And then we are trying to understand how the actively expressed genes and pathways they can act or manifest under various conditions. Moving from biofilms, let's move to the sludge. Now what happens in anaerobic digestion in the sludge? So here, Anastasia, what she does is she tries to understand how the weathering happens. So all of you know in an anaerobic digester, we have these 3 important steps in the process, from hydrolysis to methanogenesis. And there is a possibility that the microplastics sitting inside, surrounded by great nutrients, solids, microbes, contaminants, they can undergo weathering or fragmentation. And when they fragment, what can happen is their surface properties can change. There can be a localized biofilm formation. There can be release of additives, or they can be even entrapped, the microplastics. So what we want to know is which changes are the microbes responsible for out of all these listed here. And how she does is she has a reactor which is actively running. It is a semi-continuous anaerobic digester. So she does the microplastic extraction as Juvia had developed. Then she does the analysis, and she's trying to use SEM techniques, FTIR, total organic carbon leaching experiments, and adsorption. And at the same time, she wants to know if the antibiotics, which Mariam was trying to understand in the wastewater treatment, can they manifest in the sludge as well. This is our setup for the anaerobic digestion process. So you can see the different units here, the sampling port, the anaerobic fixation, and she has even developed sensor so that she can easily sense the temperature and humidity, and a stainless steel magnetic stirrer with the gas release clamp that you see here, because we don't want the gas there. Our objective is not to study the biogas production, it is to understand how the microplastics behave during anaerobic digestion. Moving forward, she is going to do some lab scale anaerobic digester experiments to understand the morphology or the qualitative and quantitative analysis of microplastics in a continuous process. So she is also going to do a seasonal analysis to understand how the seasonal variation in sludge can affect the manifestation of these microplastics. Now, last and the most important step is when you cross the final effluent, it gets to the water body. So now we were interested to know what happens when the microplastics get into Lake Ontario. So Behnam, he's trying to understand the lake stratification, The lakes during hot seasons, this is how the depth looks like, okay? You have the water mixture in the epilimnion and the hypolimnion, this is the thermocline. Thermocline is the layer which is in between, because you have water which is warm on the top and cooler in the depth. In cold season in Canada, in November, this is how the depth looks like. It's all cold, okay? So we want to understand, because the water is undergoing continuous turbulence, there is a lot of wind, okay, and other turbulence happening, which is how it is contributing to the microplastics transport. So what we do is we go to Hamilton Harbor. This is the Hamilton Harbor. It is connected to Lake Ontario, and this is the entire highway which goes to Niagara Falls. And all the site here, you see, it has heavy industry. A lot of industries here located, okay? So this is the industrial sector as well as the highway road. And we wanted to understand the vertical distribution of microplastics, about 10 micron in Lake Ontario, because no study has been reported till now which talks about temperature gradient effect on the microplastics in the Canadian lakes. So moving forward, he also had to develop a very laborious, analytical method for microplastics. He starts with Niskin bottle, because we have to take a ship, go to the Hamilton Harbor, and being university researchers, we rely on Environment Canada, that's our federal agency, who do a lot of monitoring of our waters. And the student has to go from June to November on the ship, collect these samples, then reduce the volume, okay? This is a very important and difficult step, because he gets 400 liter water at a time, and then it becomes 4 liters. So the reduction he has to do is 100 times through filtration. It's a very, very laborious step, The entire, I think, 1 month he is in the lab just filtering, doing nothing else, but no choice. And then after filtration and volume reduction, we move to the next step of ultrasonication, because we do not want any natural organic matter sticking to the microplastic. So we detach these particles from the filters, then he does the digestion, as I explained to you, Juvia had done in the wastewaters, and then he does microscopic analysis of fragments and fibers. And we also do quantitative analysis using the laser diode infrared technique, as I explained to you earlier. And we try to understand how the microplastics manifest in the lakes here. So you can see here, he's putting the device there, where the Niskin bottle, and then that will collect the sample. So normally in Canada, in the lakes, June to September, they have a very stable thermocline formation, okay? But as we get from September to October, the thermocline deepens. You know, you can see it starts to deepen. And then there is a complete mixing and breakdown of stratification. So November onwards, there is no thermocline, okay? There is no interfacial layer. And what did he observe in terms of microplastics was, you can see the abundance, that is the number of microplastics per liter, and these are the months for which he did the sampling. So he always found, you know, the fibers in large quantities. So there are a lot of fibers which are being released into the Lake Ontario. In other words, when we are talking about wastewater treatment plants and the effluent, we have also seen in the effluent, the fibers are the predominant microplastics in terms of shape, okay? So the fiber shape does not get easily fragmented because it can coil. The fiber can coil also, right? And he has seen also that as we move from summer to winter, you know, there is, even in summer, there is a high release of some of these fragments. In November also, so there is no correlation. Because we should not forget that there is a lot of recreation activity going on in summer in Canada, because we have a very narrow window when you can actually go to the beach and swim, you know. So there are many kinds of releases that is happening when people are using it for recreation on the beaches. You know, all sort of things which are releasing the microplastics. Moving further, microplastic particle type is another important thing which we found. We found that most of the particles, you know, they are, you can see this is the percentage, and we were seeing polypropylene and PL, polyethylene terephthalate in abundance, which was not the case in sludge or wastewater. So we found that particle type actually affects, you know, the type of distribution that is happening in the lake. In other words, microplastic distribution is driven by particle density, hydrodynamic forces. I'm not going into those details, but lakes and rivers have a lot of hydrodynamic forces which affect their vertical movement. Sometimes the microplastics, they form aggregates and they settle to the sediments as well. Currently, where are we? Well, this is the sampling map. This is where we sample, okay, the samples. Moving further, we study the stratified lake. So we are not able to study the low vertical mixing, but the mixing at 8 degrees Celsius, we have seen the microplastics. And then after bringing the samples, lab processing, this is where the abundance data stands. So you can see from July to November, most of the samples, you know, because it was probably easy to analyze in summer, so the abundance in depth, it increased during summer as compared to winter. Then there is another interesting thing. In addition to the sites from where we have collected these samples, you can, I don't know if you are able to see here, but this is a thin line separation, you know, in the Humber River. There is a plume, and we want to understand in the plume how do the particles they manifest, especially in the water and the sediments in the early spring, in the summer and early fall, because this is a very, you know, for a hydrological engineer, this is an interesting phenomena. So I have a colleague, Dr. Karimpour, who works around this, and she said it would be very interesting to understand in these turbulent conditions how these microplastics actually behave. So I would say the take-home message from the studies that we have been doing so far, which are still in continuity, you have the wastewater treatment plant chain here. Detection is a big thing, okay? And detection is something which we need to nail it before we move on to the next steps to understand the microplastics. And then of course biofilm transport is very important because that could also lead to the understanding in the antibiotic resistance. And microbial diversity is something which is also affected by the presence of microplastics. And last but not the least, in whichever water body the effluent is released, it needs to be understood how the microplastics mobilize themselves and partition themselves. So with this, I think I'm coming to the end of my talk. I would like to acknowledge our funding agencies, NSERC and Environment Canada, and the municipalities and other stakeholders along with the wastewater treatment plants. My colleagues, we are a big team working on this project. Everybody brings their own expertise. No single person can do a project, it's impossible. And most of all, I would say environmental related projects, they need a really multidisciplinary team to work together if you want to get fascinating results. And last but not the least, my wonderful team of, soldiers, lab soldiers, students, who continuously work to bring this to light. And I would always love to end my talk with all the mentors who have shaped my career so far in my life, starting off with my parents. This is something from India. We always like to thank our teachers, our professors, parents who are also our teachers to begin with, who bring us light and give us the knowledge to bring all this to understanding. That's all. Thank you so much. Mucho gracias. And if I have questions. I don't know. Was it working okay? I need water. Was it working okay?
Bueno.
Yeah, I'm open for question. I'm here.
Hola, buenas tardes a todos. Thank you so much for the conference. It's very important for this. In this moment, I want a present for you by the Josafat García Servín.
Thank you so much.
Thanks so much, doctor. Para concluir esta presentación de esta primera conferencia, vamos a entregarle una constancia para agradecerle a la doctora Satinder, Kaur, Brar, por la interesante conferencia que nos acaba de brindar. Thanks so much for the interesting talk.
Thank you so much to everybody, for listening patiently to me.
Para dar lectura a la constancia, es el Tecnológico Nacional de México, a través del Instituto Tecnológico de Tijuana, otorga la presente constancia a Satinder Kaur Brar, York University, Canada, por su valiosa participación con la conferencia Down to the Drain and Out of Sight, What We've Missed in the Microplastic Story, dentro del primer Congreso Internacional en Agua Limpia y Saneamiento del Tecnológico Nacional de México, llevado a cabo los días 25 y 26 de septiembre del 2025, firma el director José Guillermo Cárdenas López. Tijuana, Baja California, 25 de septiembre del 2025. Thanks so much.
Thank you.
Thank you, Professor.
Thank you.
Thank you for your participation.
Thank you.
Agradecemos a la doctora Satinder por su presentación y si alguno de ustedes tiene alguna pregunta, les pedimos, llevamos un desfase en la agenda, les pedimos por favor que se acerquen aquí al frente con ella puede platicar, es una excelente persona, puede atender todas sus dudas, obviamente en inglés. Thank you so much for your conference.
Thank you, I hope so. So thank you everybody again. Like I said, it's always a pleasure to share what we do, and I know there are many complex things when you have to present in a short while. So if you have any questions, I'm around. Feel free to talk to me, okay? It's interesting, and yeah, that's all. Thank you.
And muchas gracias again.
Como parte de las actividades del Congreso, la siguiente actividad es la presentación, discusión, para lo cual les pedimos